I want to take you back to a concept that we learned about in Physics 20 called gravitational fields. If you remember from Physics 20, a gravitational field was a line of influence that surrounded an object with mass. For instance, the Earth has a gravitational field that surrounds it. The Earth causes a gravitational field. So does the sun. So do you, for that matter, produce a gravitational field. We all have, everything with mass has lines of influence that surround it that we call gravitational fields. Gravitational fields are human-made constructs. We invented the idea of gravitational fields. We didn't invent gravity. Gravity's always existed from the beginning of the universe. We invented the idea of gravitational fields to help us to understand what's happening when there's nothing experiencing gravity. Let me explain that. Right now I'm holding a board marker in my hand. It experiences a gravitational force. So there's a force of gravity acting on this pen. The board marker is pulled down towards the Earth by the force of gravity. But if all of a sudden I take that board marker and put it away, where the board marker was at that point, there is no gravitational force anymore because there's nothing to be pulled down by gravity. But it doesn't mean that gravity's disappeared. If the Earth is what causes the gravity, then gravity still has to be there, even if there's nothing there to experience it. So we invent the idea of gravitational fields to help us to see that. We draw these field lines that surround the Earth or whatever other thing we're talking about with mass to help show us that, yeah, gravity's there even when there's nothing experiencing it. Does that make some sense? There's a force whenever you have the board marker there to experience it. When the board marker's gone, well, then you still have what we call the field, this mysterious influence that surrounds the Earth caused by the mass. In general, a field is a line of influence that surrounds something. A gravitational field is a line of influence that surrounds a mass. An electric field are lines of influence that surround an object with charge. Real similar to gravitational fields, right? Real similar. A lot of things we do with electricity are real similar to gravity. But there's one fundamental difference between electric fields and gravitational fields. Besides the fact that mass produces gravity and charge produces electric fields, besides that, the thing that I'm talking about is the direction. The gravitational field, if we're talking about mass, the gravitational field must always point toward the producer. Always points towards the producer. But if we're talking about charge, the electric field can point toward the producer or away from the producer. The reason being, there's only one kind of mass. It's, for lack of a better term, positive mass. There are two kinds of charge. So if you've got one kind of mass producer, you're only going to get one direction of gravitational field. If you've got two kinds of charge producer, positive and negative, then you're going to get two directions of electric field. We'll talk more about when it's toward the producer, when it's away from the producer in a few minutes. Okay? Right now, it's real similar to gravity in all the stuff we've talked about, except the direction can be opposite. The direction can be toward the producer or away from the producer. Just like gravity fields, electric fields are vector fields. Means not that they travel in a certain direction, but rather that they influence in a particular direction. Our gravitational field lines are drawn toward the producer, toward the mass. Our electric field lines are drawn toward or away, which means they influence objects in a particular direction, either toward or away from the producer. Therefore, vector fields. Unlike a scalar field, for example, a light field or a heat field that has an influence on things, but doesn't influence things in a particular direction. So when you look at the light bulb right now, that influences us, right? Influences all kinds of things. It causes plants to grow. It changes our mood. It influences all kinds of things in all kinds of different ways. But none of those influences are directional. None of those influences are toward or away or whatever. They're all influences, but scalar influences. Therefore, we call a light field a scalar field, or a heat field the same thing, a scalar field. Doesn't mean that they don't travel in a particular direction. Light does, right? Turn on the light bulb, it goes from there, that light bulb, to your eyes. It moves from there to here in that direction. But that would be the velocity that we would say is a vector, the velocity of the light that's a vector, not the field itself, because the influence of the field isn't in a particular direction. I wouldn't lose too much sleep over that, because honestly, what we're going to focus on in this unit is, of course, electric fields. We'll talk about gravity fields a little bit, but mostly electric fields. And both of those fields are vector fields because they provide that influence in a particular direction. Just a little bit more background before we start drawing a few pictures of these fields and defining direction. Talked about this with gravity, right? Fields exist as long as you have something to cause it. That's the whole idea behind creating the idea of fields, right? Creating the concept of fields. We have to have some way of describing the influence without having anything to be influenced. We can talk about gravitational field even if the board marker isn't there. All we need is the Earth to cause the gravitational field. We can talk about the influence of an electric charge or the electric field that surrounds an electric charge, even if there's nothing there to experience it, as long as we have something to cause it, the producer. So the field exists as long as there's a producer. However, forces don't. In order to have an electric force or a gravitational force, you have to have something to cause it, but you also have to have something to experience it. So the field requires, if we're talking about gravity again, just the Earth. The force requires the Earth and the board marker to experience the field caused by the Earth. Electricity, a field requires just a charge to produce the field. A force requires another charge to experience the field, to be pushed or pulled as a result of that field. If the electric field is a vector field and it has a direction associated with it, then we have to define that direction. The direction of a gravitational field, listen carefully to this, is the way that a mass would move if placed in the field. So think about that. Okay, here's the Earth. If I put a board marker above the surface of the Earth, it would be attracted to the Earth. The board marker would move towards the Earth. Therefore, we say the direction of the field is toward the Earth. It's the way that a mass would move if it was placed in that gravitational field. We're going to define the direction of an electric field as the way that a positive charge would move if placed in the field. The way that a positive charge would move if placed in the field. So let's look at a couple scenarios here. We could have a positive producer. If I put a little positive charge in the field caused by that positive producer, which way would it go? You know the answer to this question, right? Here's a positive, here's another positive. The green one is going to go this way, or this way, or this way, or this way. The electric field surrounding a positive will go outwards, away from the positive, because that's the way that a positive would move if placed in the field. If I have a negative producer, and we put a little positive charge in that field, it would be attracted towards it. So we say the field surrounding a negative is toward the negative, away from positive, toward the negative. We're going to define it as the way that a positive particle would move if placed in the field, but we could also say it's away from a positive producer and toward a negative producer. Have a look up here, guys. This is a little applet that shows us the electric field that surrounds different charges. You can see that the electric field here is caused by a positive producer. So this is a positive source, which if I put a positive test particle somewhere in there, like right here, let's say, it's going to go away from it. It's going to be repelled by it, right? That means the electric field points away from the positive producer. So usually when we draw it, we draw 2 or 3 or 4 or 5 field lines, right? I use this applet just to show you that, first of all, The field lines go out in every which direction from it, but they're all pointing outwards. Now, I wish I could show you that it's also three-dimensional. It's not on a two-dimensional plane. If you have a globe, it goes out in every which direction in 3 dimensions from it as well. Let's put in another charge here. Let's call it a dipole. A dipole has a positive and a negative. You can see in the first one that the field lines point away from the positive everywhere, right? Away from the positive. And the negative, they all point toward the negative. Well, if you look at in between, it's kind of neat what happens in between. The field lines that leave the positive right here, field lines that come into the negative right here, end up joining up. So you see this kind of neat pattern here that forms from the positive toward the negative, from the positive toward the negative. Okay, that's what the field will look like surrounding a dipole, a positive and a negative charge. If we have two charges that are the same, a double charge we'll call it, the pattern here is kind of neat as well. You can see that the field lines point away from the positive, point away from the positive in the bottom one, okay, in every which direction. But look what happens in the middle. The field lines, as they approach each other in the middle, repel each other. So they kind of go like, oops, now they go apart from each other, as opposed to joining up like they did in the last diagram. Make a little bit of sense? I'm going to draw these out as well, so don't panic about trying to represent what you see on the board here on paper with your own drawing. I'll draw them out in a little bit of a simplified manner. I just wanted to show you a better representation of what it looks like with field lines going everywhere as opposed to just a few field lines that I can draw on my paper. Okay, remember this though. Okay, remember this one big important part of this. If field lines join up like they do with the dipole, then the charges will attract. If the field lines don't join up like they did with the double charge right here, then the charges repel. Now, when we look at a diagram of two positives or two negatives, it's pretty clear that they're going to repel, right? But sometimes you have a diagram that's a little bit trickier, right? It's a little bit trickier to interpret. The way you determine whether they attract or repel, if it's more complicated than what you see right here, is look at the field lines. If they join up, they attract. If they don't join up, they repel. Make sense? Somebody's hand was up a second ago. Two people's hands up a second ago. Okay, Mac and Christian. If you were to put a neutral particle, that's a good question. If you were to put a neutral particle right in the center, would it be affected by a field? No, it would not. If you were to put a positive right in the center, it would not be affected. If you were to put a negative in the center, it would not be affected. Nothing would be affected right there. Here's why. Okay, think about it in terms of fields. First, there is no field right there, right? They've all repelled each other to the point where the field in that spot is zero. There's nothing there. Now let's think about it in terms of forces. If you have, let's say, a positive in the middle, it experiences a force as a result of the top one. It experiences a force as a result of the bottom one. They're going to be opposite directions. They're going to be equal and opposite, if these charges are equal, that is. And therefore, they're going to balance each other out. So there will be no force. If there's a charge there with no force, then the field must be zero as well. So, field is zero. Right there in the middle, the field is zero. Nothing is affected by it. Yep. Christian? No. One of our quizzes, we had a option D, I think, that talked about magnetism. We haven't learned about magnetism yet. I told you, when you see something like that on a quiz or a test, it's not the answer if we haven't learned about it, right? We will talk about magnetism, but electricity and magnetism aren't the same thing. So when you talk about positive and repelling each other, like we want to start thinking, oh, okay, you know, where does that apply? And maglev trains, perfect example, right? No, that's a force of repulsion, but it's a result of like poles of magnets repelling each other as opposed to like charges repelling each other. And there is a relationship between magnetism and electricity, but they're not the same thing. Okay? Positive charges are not north poles, and negative charges are not south poles. So we can talk about that a little bit more when we get to our magnetism unit next unit. Good question too. Yep. Yep. Oh, look at that. Good question. That's a good question. Let's go back to this for a second. What if we were to put a negative particle right here? what would happen to it? Go towards the positive, wouldn't it? Because negative and positive attract each other, right, Greg? Does that mean we have to reverse the direction of the field? Not at all. We define the field as the way that a positive particle would move if placed in the field. We have to define it one way, right? We have to pick a way. It's an arbitrary definition. We could have just as easily said it's the way that a negative moves when placed in the field, but we didn't. Okay? Somebody, sometime, defined it as the way that a positive moves, so that's what we go with. A negative moves, positive moves with the field, negative would move opposite to the field in all cases. Take a look at this. You're going to get a question almost exactly like this on your unit test. Here's an electric field. I don't even remember on your unit test which way the field's pointing. Okay? We'll say to the right. You get a negative particle, a positive particle in that field. You get a negative particle in that field. What's going to happen to those two particles? Well, what caused the field? Was it a big positive over here? I don't know. Doesn't say. Was it a big negative over here? Could have been. Could have been the negative and a positive, right? Because the field goes away from the positive toward the negative. We don't know what caused it. It doesn't matter. It doesn't matter what caused it. We know that positives will experience a force with the field, and we know that negatives will experience a force opposite to the field, regardless of whether it was a positive that caused it, or a negative that caused it, or both that caused it. Does that make sense? So back to your question, simple answer is put a negative in there, experiences a force opposite to the field every single time. Opposite to the field itself. Because we define the definition, the definition of the field is the way that a positive would move, so a negative, by definition, must move opposite to that. Okay. Let's draw a few of those diagrams here in a little bit simpler way. It's not as good of a way. Okay, it's not as accurate of a way as that applet that I showed you, but it's a little bit easier to see and a little bit easier to draw for you in your books. Surrounding a positive, field goes away, right? Why? Because if we put a positive test particle in that field, it's going to go away from it. Negative goes towards it, because positives would move toward the negative. What if we have a positive and a negative close enough to each other that they interact with each other? Field lines go away from the positive. Oops. Away from the positive. And they go toward the negative. What's the neat pattern that we see as a result of that? Well, the field lines end up joining up. Remember, when the field lines join up, there's an attraction. Force of attraction between whatever it is that's causing that field. If we have two like charges, say two positives, field lines will go away. Kind of get messed up in my field lines, but that's okay. They're all pointing away, so that's all. It's all good. These field lines are going to go like this. They're never going to join up. Next question about what happened to something in the middle there? Nothing, because the field lines have all repelled each other to the point where there is no field in the middle there. How would this diagram change if I change those charges to two negatives instead of positives? It's not going to change dramatically, but there's going to be one fundamental difference. Exactly. It looks exactly the same except the arrow's in the opposite direction. The net effect in the middle would still be no electric field. It wouldn't affect a positive, a negative, or a neutral in the middle. Finally, this is where I want to end off today. Three equations that you saw in Physics 20 that represent gravity and gravitational forces and fields. Let me refresh your memory as to what each of those means. F is equal to gm1m2 over r squared is the gravitational force between two objects with mass. The electrical equivalent to that is F is equal to K Q1 Q2 over R squared. This is the electric force between two objects with charge. You can see the similarity between gravitational force and electric force. The next equation is for gravitational field. If you have information about what caused the field, the producer. If you don't have information about what caused it, if you have information about what experiences the field, then that's not a good equation to use. If you know what caused it, you have information about what caused it. Let's say the Earth causes the field that influences the board marker. Well, if we know the mass of the Earth and the distance from the center of the Earth that the board marker is away, then we can use this equation. This is the symbol for electric field. Don't forget that vector sign over it. I can live with it if you forget the absolute value signs. Don't forget the vector sign. Okay, I guarantee you this. Every single one of you in this room will mix up electric field with energy if you don't put the vector sign over top of that. Right now, you might not think you will because it sounds like it's something completely different. I'm telling you, I promise you, every single one of you, if you consistently leave off the vector sign, will mix up energy and electric field. This is how we distinguish electric field from energy. We put the vector sign over it. If you put the vector sign over it, you still might get it mixed up. But if you don't, you will get it mixed up. So don't forget that vector sign. Tell me what the equation for electric field caused by a producer is. You know this, or at least you can figure it out. Jotham? Good. KQ over R squared. Q would be the charge of the producer in coulombs. And R would be the distance from the center of the producer. And that's going to, of course, be measured in meters. All right, the next equation that we see down here is the gravitational field if we have information about the experiencer, the board marker. The force experienced, the mass of the experiencer. Tell me what the electrical equivalent is going to be, Matt K. E is equal to, not F over R, F over, yeah, F over Q. F would be the force experienced. Q would be the charge of the experiencer. And that's going to be in coulombs. Here's one quick example. Notice we're in chapter 11 now. One quick example, page 548 says, a sphere with a negative charge of 2.1 times 10 negative 6, draw attention to that negative so I don't forget, experiences an electrostatic force of repulsion when it's placed in an electric field produced by a source charge. What's the electric field that the source charge produces at the sphere? So look at this. This sphere experiences a force. This sphere would be the experiencer. This source charge would be the producer. It's what causes it. What do we know more about? The producer or the experiencer? To go back to the analogy we used, what would we know more about? The Earth or the board marker? What causes the field or feels the field? Yeah, we know more about the experiencer, right? So let's use the experiencer equation here. Let's write down a couple givens first. Q of the experiencer, negative 2.1 times 10 to the negative 6 newtons. The force experienced is 5.60 times 10 to the negative 2 newtons. Sorry, that charge should be in coulombs. We want to know the electric field. Experiencer equation, F over Q. We're going to say 5.60 times 10 to the negative 2 newtons over 2.10. Remember, drop the sign of the charge, right? Do the math there. So this for a second. Do the math there, and we get 2.7 times 10 to the 4. That would be, look at the units, newtons per coulomb. Is that okay? If we knew something about the producer, we'd get the same answer. Okay, what's the field experienced by this board marker right now? 9.81. What's the field caused by the Earth at that point? 9.81. Just because you have more information about one than the other doesn't mean you're going to get a different answer. It just means that you're going to use a different method. That's all. All right, your homework for tonight were those check and reflect questions that I assigned. You finished about half of them. In addition, questions 1 and 2 on page 148, please. Sorry, 548. All right, that's it for tomorrow.